it's got the best potential, you know, model of the atmosphere as it was for use in something like machine learning surrogate development. So.
All right, so we need to move to our next speaker. That's Enrico, and we're going to talk about data assimilation and machine learning for space weather.
All right, so hello everybody. My name is Enrico Camporeale. Thanks a lot for having me. So I was tasked with talking about machine learning and data assimilation in space weather, which I thought, sure, I can do that easily. And I thought, well, 20 minutes, maybe keep it to 15. So I kind of bailed out, and I thought I couldn't do that without giving a lot of equations and stuff. So so I kind of changed the title now to some kind of random thoughts about around machine learning data assimilation. I promise if I get time, if I manage to have one last slide actually talking about the similarities and conjunction between machine learning and data assimilation. But most of this talk, and I apologize that I've presented this stuff a number of times in different venues, so some of you might be familiar with this, but I thought more of giving a context. And I will talk a lot about machine learning, less so maybe about data assimilation. So what I would like to start with is this paper published in 2007 by George Cisco in this monograph, Space Weather, Physics and Effects. It's a nice book. So George Cisco was a kind of a giant in the 90s and 2000 in magnetospheric physics. He passed away, I think, 2 or 3 years back. And the reason I'm starting with this is because I kind of believe that it's a good exercise for a scientific community, for any scientific community, maybe every 20 years or so, to pause and go back and ask ourselves, how did we get here? What was the rationale, the narrative, and so on. And for people that have been working in space weather, we know that the narrative for the last 20, maybe 30 years is that space weather is the younger sibling of meteorological weather. And this is very well, the reason I'm putting this up is because it's very well described in this paper, which is called Space Weather Forecasting View Through the Lens of Meteorology. And let's see if this works. So I'm just going to read briefly the highlighted part. So again, this was the school of thought about 20 years ago. The advent of physics-based numerical space weather prediction is still in the future for space weather, although codes to achieve such predictions are under development. So this was really the start when the community started working on physics-based code to do space weather prediction. And then again, the narrative was because we already in 2007, numerical weather prediction was so extraordinarily successful that we thought, okay, we're just going to follow the footstep of numerical weather prediction, and we're going to have a great result as well. And another interesting paper, this is more recent, it's 2015. This is very famous review paper published in Nature, which talks about the quiet revolution of numerical weather prediction. And I strongly suggest to read this paper if you haven't done so already. Basically, the authors kind of identify of course, it's a very technical field, but the 3 main ingredients of why numerical weather prediction has been so successful. And I mean, somebody could argue, and the authors themselves argue, that it's one of the greatest achievements of humanity, of science, that we are able to predict the weather, right? And basically, the 3 main ingredients are the following: physical process representation, ensemble forecasting, and model initialization. And I'm going to get later on back to AI in weather prediction, but just want to kind of a pointer to these 2 YouTube video, if you have the time, that explain. So this one, it's very nice. It's called The Quiet AI Revolution in Weather Prediction by Richard Turner. And the second one is by Pedram Hassanzadeh, AI and the Second Revolution in Weather, again, brought by AI. And so this is the reason of why there's been this quiet revolution. It's because, so this is it's a bit of technical, but basically it's the accuracy of numerical weather prediction 3, 5, 7, 10 days ahead in the northern and southern hemisphere. And this is sort of a Forsker scale score. And you can see that from the 80s, basically in the last 40 years, there's been a continuous improvement to the point where 3 days ahead prediction now is accurate on average, of course, about 98, 99% of the time. So once again, for the last 20 years, the accepted narrative in my community, in the space weather community, was that space weather is a younger sibling of terrestrial weather. As such, the hope has always been that space weather will soon achieve the same level of extraordinary success that we have seen in numerical weather predictions. And as a consequence, if you wish, the majority of effort and funding has been spent in developing physics-based models. Now, I think after 20 years or more, I think we have to kind of do a reality check. And this is kind of my opinion, if you like, but I believe it's well kind of documented opinion, is a physics-based model have not so far delivered what was expected 20 years ago. And this was touched a little bit by Tom earlier on. Pretty much none of those models have a strong accuracy or strong skill. So to me, the fundamental reason why in the Sun-Earth system, a physics-based model will actually never, and this may be a bit of a pessimistic view if you wish, but will never reach the required level of accuracy, is because, again, going back to these three fundamental ingredients that are the reason why numerical weather prediction works. So let's look at those one at a time. So one is physical processes representation, also known as subgrid modeling in numerical weather prediction. So to the left, we have the meteorological weather, and to the right, the space weather. So the state-of-the-art numerical weather prediction right now can solve a grid to the level of 10 kilometers. And what subgrid modeling does is to add the physics, which is not in the model, and there's about 1 or 2 orders of magnitude missing, meaning that you get down to 10 kilometers, you want to capture things that happen at a 100-meter level. So it's 1 of 2 order of magnitude per dimension. So it's challenging, but it's done. And that's what operational numerical weather prediction does. Now, I don't know how much you're familiar with plasma physics. I didn't even know what number orders of magnitude to put there. It's about maybe 7, 8, 10, I'm not sure, just as a kind of a figure of merit. So basically, what we're missing in the global 3D MHD model is all the kinetic physics. And the kinetic physics is what dominates magnetic reconnection and all the stuff that are important for substorms and so on. So just to give you an idea, the electron gyro radius in the magnetosphere is about 1 kilometer. And the Debye length, although not much physics happens at the Debye length, but oftentimes you need to resolve this for numerical stability, this is about 10 meters. So again, I have no idea what kind of, or how many orders of magnitude you need to cover with subgrid modeling, maybe 7 or 8 per dimension. Another thing is this ensemble modeling. So taking as a sort of a key reference, the ESMWF, they run an ensemble of 51 forecasts with a horizontal resolution of 9 kilometers. So there's one control forecast plus 50 forecasts, and this is kind of standard ensemble modeling. Each forecast is has a slightly perturbation, both on the observation and on the model. So observation errors are represented by perturbing the observations, and the model errors are represented just perturbing the parameters in the forecast. Now on space weather, unfortunately, we have no idea of what our observation, particularly remote observation, like these beautiful images that Tom showed of the sun. We have no idea how much the error on those observations are. And on the other side, maybe this can be quantified in the future, but we have no idea about the model errors in our models. And then finally, maybe more importantly, the workshop is about data assimilation. And as you people working in atmospheric science know, there's a lot of data in numerical weather prediction. So again, those are figures. I mean, the actual figures are not important. It's more of an order of magnitude, but I took this from the ESMWF website. They ingest daily 800 million observations, and really out of those, the high quality data or post-process that go into the data simulation are about 60 million points. Now, there are different ways to do data simulation in space weather, and I believe we're focusing here on ionosphere, and that can be done to some extent. But if you think about the driver, and again, Tom described this very well, everything is driven by the solar wind. We have one data point of solar wind observation, which is our satellite IL-1, that gives us about, I'm not sure, 6, 7 numbers. So with these 6, 7 numbers, we are trying to model all the boundary condition of a complex giant 3D model. So again, it might be a bit of a pessimistic view, but I think it's a bit of a reality check. So this is the state-of-the-art operational physics-based model running on Zwipsy. Those are all been mentioned before. So WSA Enlil, Geospace, and WMIPE. So what this table does, I'm not going to spend too much time on this table because I know that people get upset, but there are, to me, at least 3 characteristics that makes a model a forecast, right? In order for a model to be a forecast, you need to have enough lead time. You need to be able to predict some in the future. Your model output needs to be actionable, which is a combination of lead time and uncertainty quantification. And then, of course, it needs to be accurate, whatever accurate means in that given context. And then on top of that, kind of a secondary consideration, if you wish, there is the cost associated with running the model. Now you can see that none of the physics-based model running as Zwipsy check. So obviously the red means it doesn't check, and the green it means it's doing all right. So none of the model can be properly called forecast because they don't check all the boxes. On the contrary, this is really what machine learning can do. And again, in my opinion, many other people's opinion, machine learning will really become the standard way of doing space weather forecasting, probably by the end of the decade, so in about 5 or 6 years. And that's the reason. I mean, machine learning, you can pretty much specify whatever lead time you have, as long as you believe that there is an information flow between your input and output. And there are a number of papers in the literature showing a 1 hour up to 3 days forecast. Machine learning models are actionable because you can easily build an ensemble of machine learning models. Some more sophisticated machine learning has some sort of UQ, uncertainty quantification, sort of built in the model. So that makes it actionable. And then the accuracy, again, I mean, this is, I can talk for hours about this, but pretty much all of the stuff which has been published in the literature show that the accuracy is typically better than physics-based equivalent. Now, again, the cost is a secondary consideration, but Tom mentioned LiveDST, which is a model we run kind of real time at CU to predict DST up to 6 hours ahead. The cost of that stuff that runs on the cloud is $10 per year. So Tom is paying out of his pocket for this, basically. All right, so these are all stuff that, as I said, I kind of, to some extent, presented already in some other venues. And I think I still stand by all these opinions, but something I wanted to mention now in the last few minutes I have is that things have changed considerably since about 2023 in the world of numerical weather prediction. And this is a slide that I obviously borrowed or stole from a YouTube video. And there has been a sudden explosion of AI for weather prediction, for meteorological weather. And so what this plot shows is a number of different models as a function of time on the horizontal axis. And what is shown on the vertical is the relative skill with respect to numerical weather prediction. So basically, when you go over the 100%, this is the breakthrough where AI does better than a physics-based model. And there are a lot of caveats. It's hard to compare apple to apple and so on, but this is kind of the overview. And what is interesting, what I would like to point out here is that the previous plot I showed about this improvement of numerical weather prediction, there was a 40 years long plot. It's been a continuous improvement over the last 40 years. This plot here covers 5 years. So in only 5 years, we got to the point where now the most modern AI model do better than physics-based model. A more kind of comprehensive view here is a web page called WeatherBench 2. It's hosted by Google. And here you have a more comprehensive comparison between physics models, these 3 here, for different lead times and different quantities of interest, versus machine learning or hybrid models, where basically blue means that the model does better in that given parameter than a physics-based model, and red, it does worse. And I think one of the best right now, there is an operational version of GraphCast that the ECMWF actually runs on their website. And this does better, at least better than the single physics-based model, the mean of it, not the ensemble. All right, so I promised that I will talk about DA and ML, and this is the one slide. So there's a lot of discussion in the community, in both communities, I believe, in the DA and machine learning communities, which historically has kind of grown separate. There's a lot of discussion of how, obviously, each method is very powerful and has been used to a great success, but how can one method help the other? So to me, what is kind of striking are the kind of the differences. I mean, there are a lot of similarities, something that if you read papers, you realize that the Kalman filter in DA is pretty much the same math as Gaussian processes in machine learning. So there's a lot of overlap in methods. The data simulation has been designed always with the, keeping in mind that you want to apply DA on top of a physics-based model. So it's designed to provide the optimal initial state at one given time for a forward model, right? So kind of your state model. Because when you talk about physics-based model, it's always an initial value problem or a boundary condition problem. So you only care about the optimal state at that one given time. This is kind of a complete opposite of the paradigm of machine learning, where in principle, it might be hard to train such a model, but in principle, it can map a time series of observables. So if you think that, there are 2 days of observables that are useful to forecast this one quantity, you can ingest all of that and try to map. I mean, all that machine learning does is really to find a function or a map between multi-dimensional variables as an input and some other possibly multidimensional output. So this is to me the biggest difference. And there are other differences that the state variables, lost my pointer here, but okay. State variables in DA are not necessarily all observables. This is possibly one of the major advantages of DA. There's this observation operator or projection where, some of the quantities that go into your model might or might not be observable. They might be, it's very good, DA, it's very good to deal with sparse, irregular, and noisy observations. Machine learning has a lot of trouble dealing with that. There are ways, but it's not definitely you have to do interpolation, filling gaps, and so on. On the other hand, DA relies, I'm not an expert really, but from all the papers I've read, relies always on a number of simplified assumptions, whether it's linearity, Gaussianity, and so on, while machine learning, at least in the version of completely data-driven machine learning, there are very few assumptions. Now, a kind of exploding field in the machine learning community is physics-informed machine learning. So how can you kind of ingest some physics constraint into your machine learning? So that would give you some assumption. And then finally, assertive quantification for machine learning is still very much an open challenge. There's people doing their PhD thesis on that very topic. It's not yet clear how to do that properly from first principle, but it's something people are working on. Kind of the point of conjunction between the two, again, taking the numerical weather prediction as our example, is that all those models that now are beating NWP are actually trained on the reanalysis of NWP. So that's where the data simulation helps into creating, like you might be familiar with the ERA reanalysis data set, and that is used as your training set for machine learning. So the way I believe that the space weather community should really go to is to create those reanalysis data set for whatever problem we want to solve, and use that to train a machine learning model as a surrogate of your physics-based model. That's all I have. Thanks.
I mean, I could have probably talked another hour with you just on the stuff that you talked about. So it's
Let's not
very
do
good
that.
talk. It gets me.
There is lunch. So.
Gets my heart pumping so bad. But I have just, I'll make 2 comments, just 2 comments and be a question. Once, I guess you started by talking about the Cisco paper of 2007, I guess, but there's a 2006 one with Solomon that actually does distinguish the, just say that, you do have a terrestrial sort of a mimic for how space weather could go about. But there is also a part of it because of time scales and not that cannot follow the terrestrial model. So it's recognized there already, the distinction between 2 parts of space weather. The other thing that I was going to say is that referred to the last line here. And is that you mentioned that ML or the machine learning approach has in the 5 years or so has, it's evolved so fast, so much faster than the weather prediction system that's taken so long to evolve. The fact is that they did so because of exactly your last line here. It had already this effort that's being done for so long, and you could rely on that. So all these models are trained on reanalysis. So if you don't have that, how do you go about that, the ML models? So, you have to take that into account as well, no?
Sure, I think that's a fair point. So you're saying that this 5 years of effort have been built on the previous 40 years of reanalysis and so on. Fair enough. Still, it's true that so they had all the ingredients ready, but
Other thing I'll say is this: in 1994, I'm old enough to have been there in a conference where it was the first time where the ensemble Kalman filter was sort of talked about more openly. I mean, it was coming out as this hot thing, and nobody believed on that. There was like a conference where 95% of the people were saying, no, this is just a Kalman filter is the thing, or variation of DA is the thing. And so they were seen as completely different things that were completely different worlds. And I think that we are at almost this stage with ML, where, I mean, some people have already realized that the best thing is to hybridize things, that one approach can benefit from the other. And that's what happened to the ensemble approach. The ensemble approach became joint with, was joint with variation approach, traditional approach, and now it's one thing. So I think ML is already happening, right? Because a lot of these physics-based ML and stuff are doing that. And there's a lot of stuff already happening in the JEDI to incorporate the stuff in. So I think the hybridization is really a more likely thing to happen in my perspective.
That's a great point. I had exactly the same image in mind, like the variational versus ensemble, and now everybody's doing INVAR somehow. And here, I'm sure, everybody will be doing demo, DA and ML, hybridized.
First, I need to make a quick comment. For people, if you are using that pointer, if you couldn't find it, imagine there is another monitor on the side. There is another, or actually over the back. So the pointer sometimes go to that window. So you just horizontally move it back and you will see it. So, okay, my question for Enrico is that, so we are, a lot of machine learning models using reanalysis, which is, ERA. But ERA itself has physical constraint and using a lot of data and analysis system. So we are running in a circle, because if we are keep training machine learning models using reanalysis, we are limited to the model and analysis system flaws from ERA as well. So they can at times looks good, but on the other hand, think about ERA people, what they do, right? So there is still behind it, there is the model and the physical model and analysis system behind what's being achieved at this point. But leaving that aside, for space weather, there is machine learning stuff. I would like to hear from you is, with limited data, much less data compared with neutral atmosphere, then our training for the machine learning would be limited as well. How do you envision that work coming to space weather using machine learning method?
I'm sure I understand the question. So how do you envision using the kind of
limited data?
the data?
Yeah, for the space weather, right? It seems what I heard from Shuwei, for example, there's limited data to measure the wind changes when it comes to storm, etc. So you would have limited information. You would have information for certain variables, physics, but you will have missing information from some other part.
Well, my understanding is that it's true there's limited real-time data, but I think, still probably talking orders of magnitude less than what we have in atmospheric science. But I think if, in some context in space weather, it's a lot of chain of things, of events, but there is a lot of historical data that we can use and people have used to train models. So in fact, in some contexts, we might even have too much data. I mean, SDO archives petabytes of data. Now, one challenge is how to, now, if you take the assumption, which is the same assumption that physics-based model use, that there is information in the solar images to drive a model, because that's, for instance, what the WSA Enlil does. They use magnetograms and drive that as a boundary condition. So if there is information in the solar images to tell us what's going to happen on Earth like 2 or 3 days later, the challenge is really how to extract that information from the petabytes data that we have. You know, SDO takes 4,000 square image every 12 seconds. So it's a problem of noise to signal that, I mean, from a machine learning perspective, it's a beautiful challenge to address. So I think that, yeah, I'm not sure whether that addressed your question. A different problem is whether you want to add the DA component on top of whether a physics-based or machine learning sort of forward model, because then, yeah, you need some real-time observation, which we might not have at this point.
So we'll take one last quick question, and then we need to move on.
Okay, I'll make it quick, but you already touched on this. Nice talk as always. But in terms of, I often hear with regard to data assimilation, space weather, lack of data as a problem. But as you said, SDO takes 4,000 by 4,000 images every 10 seconds in 10 wavelengths. A single image is 16 million data points. And yeah, that's not real time now. But the amount of data of coronal AIA data that we're using at SWIPC to forecast the solar wind is 0. So there is a potential there. The data is there. You have to pick your battles. You know, use the magnetosphere as an example. That's sort of a worst case scenario. But in terms of data on the solar surface and the solar corona, there's no lack of data there. I would say that we have a lot of data there, and there's a big potential for DA. Yeah,
I agree. I completely agree. Now, the data on kind of downstream, they might maybe be used for data simulation, talking about, think about magnetograms. Again, it might not be the amount of millions of data points we have for Omega weather prediction, but we have hundreds of magnetograms on the ground. We have GNSS data. So there's a lot of data that can be integrated and simulated at one given point. And yeah, as you said, the input, the driver, it's a huge amount of data as well.
Thank Enrico again,
Thank you.
and move on to the next speaker. It'll be Dave Kuhl talking about the NRL effort in ionospheric DA.
Do it pointed over there and then I go here. Oh, that works. Oh, that's good. Okay. So, and then I went back. Okay. Thank you all for having me up here, and kind of hard to follow Enrico's presentation because I am using physics-based models and trying to do data assimilation. But I think I'm going to try to argue that the area that I'm interested in, I think there is there's some room for some improvement, and that we might be able to get something out of it. So I work